So have you ever really thought about what makes Java tick? I mean, how does it run on literally billions of devices, from these huge cloud servers all the way down to tiny little smart cards? Well, the secret sauce is this incredible piece of engineering right at its core. And today, we're going to take a deep dive into that very heart of Java, the Java virtual machine.
Ah, yes, this famous line. This is the legendary promise that basically put Java on the map. But think about it. How is that even possible? How can the exact same code you write on your machine run perfectly on a Mac, a Windows PC, a Linux server, you name it? That's the big mystery we're going to unravel right now.
All right, to get to the bottom of this, we're going to follow a piece of code on its entire journey. We'll start with that big promise, then see how our code gets turned into a universal language. From there, we'll watch it enter the virtual machine, see how memory gets all set up for it, and then, finally, we'll see the execution engine bring it out to life. And at the end, we'll talk about why this whole thing still matters so much today.
Okay, so let's get right into that central question. You know that different computers speak different languages, right? A program compiled for Windows is just gibberish to a Mac. So how on earth does Java just sidestep this fundamental rule of computing?
Well, here's the secret. Java code is smart. It doesn't even try to talk directly to the operating system. Instead, it talks to a middleman, this universal translator that lives inside a virtual machine running on your computer. And that is the JVM. It is the key to absolutely everything.
So before the JVM can start doing its thing, our human-readable Java code, the stuff we actually write, has to be translated into a language that the JVM can actually understand. Let's look at this very first crucial step of the journey.
It all kicks off with our standard .java file, right? But here's the twist. When you hit compile, the Java compiler doesn't create native machine code for your specific computer, nope. Instead, it creates this universal, intermediate set of instructions called bytecode. This bytecode gets saved in a .class file, and you can think of it as the universal language that any JVM on any machine in the world can understand.
Okay, so now we have our portable class file. It's ready. It arrives at what you can think of as the front door of the JVM. And this entrance is guarded by a really important component called the class loader subsystem. Its entire job is to take our bytecode and get it properly prepped for execution inside the virtual machine.
Now, the class loader is super careful. It doesn't just jam the code into memory. It follows this very specific three-step process. First, it loads the file from the disk. Then, it links the code to make sure everything is valid and all the connections are in place. And finally, it performs the initialization, which is the last step to get it ready to run.
Let's zoom in on that linking phase, because the first step here, verification, is basically a critical security checkpoint. The JVM painstakingly inspects every line of the bytecode to make sure it's not trying to do anything illegal or malicious. If the code is shady, it gets stopped cold, right here. This verification step is a huge reason why Java has such a strong reputation for security.
All right, our code is loaded. It's been verified. It's legit. So now the JVM needs to set the stage for the performance. It does this by carving out some very specific memory spaces, which are called runtime data areas, to organize all the data our program is going to need.
First step is the method area. The best way to think about this is as the application's library, or maybe a blueprint room. It's where the JVM stores all the class-level information. You know, the actual definitions of your methods and variables. It's a shared space, so every part of your program can look up the blueprints here.
Next, we have the big one, the heap. If the method area is the blueprint room, the heap is the main workshop. Whenever your code actually needs to create a new object, like, say, a user profile or a shopping cart item, it gets built and stored right here in the heap. This is the largest memory area and, just like the method area, it's shared by all the different threads in your program.
Now, unlike the shared heap and method area, every single thread of execution gets its own private stack. You can picture the stack like a personal to-do list for that one thread. Every time a method gets called, a new frame is pushed onto the top of the stack. This frame holds all of its local variables and keeps track of where it is in the process.
And this brings us to the core principle of how a stack works. Last in, first out, or LIFO. Just think about that to-do list. If you're working on one task and have to start a new, more urgent one, you put it on top. You have to finish that new task before you can go back and finish the one underneath it. That is exactly how the stack operates.
Okay, let's recap. The code is loaded. It's been verified. The memory areas are all set up and ready to go. The stage is perfectly set, so it's finally showtime. It's time to meet the star of the show, the execution engine. This is the part of the JVM that actually runs our bytecode.
So the execution engine has this really clever two-part strategy. First, there's the interpreter. Think of it like a live translator, reading the bytecode and executing it line by line. It's awesome for getting the program up and running instantly. But if it has to run the same piece of code over and over, it can get a little slow. That's where the just-in-time or JIT compiler comes in. It's always watching, and it identifies these hotspots, code that gets used a lot, and compiles them directly into super-fast native machine code on the fly. This dynamic duo gives Java the best of both worlds, a quick start and incredible performance over time.
So there you have it. We've followed our little piece of code through its entire journey. We saw it get compiled, loaded, verified, and finally executed. Now let's just zoom out for a second and look at the big picture. Why does all of this incredible complexity matter so much?
Well, what's the big takeaway from all this? This whole architecture gives us 4 amazing benefits. First, platform independence. It's what delivers on that write once, run anywhere promise. Second, serious security, thanks to that tough bytecode verifier we met at the door. Third, automatic memory management. We didn't even talk about it, but there's a component called the garbage collector that automatically cleans up the heap for us, which prevents a ton of common bugs. And finally, of course, high performance, all thanks to that brilliant JIT compiler.
The JVM was, without a doubt, an innovation that completely changed software development. But now we live in a world of Docker containers and cloud-native apps which, they provide their own kind of run-anywhere abstraction layer. So it really makes you wonder, doesn't it? In this new world, what is the future role for a virtual machine that runs inside another virtual environment? It's definitely something to think about.